not going to go through all of them. There'll be some in here that I'll just go through and just leave it for you to go at your own pace. A couple of example problems. I might spend a few minutes on the radioactive decay. There's one on there on a cantilever beam. It gets too much detail in there and we chew up too much time. And then at the end, we'll talk about some of the research that Shaling and I have been doing with regards to particle dispersion. Remember the popcorn experiment?
Yeah.
Yes. And actually, we pulled that off quite well at the Marriott. It went really nicely. So we'll talk a little bit about what we're doing with regards to particle dispersion and so forth. One of the problems, the second problem there, actually deals with a particle movement within a room. We'll talk about it at the end. I wanted to at least make you aware of Monte Carlo simulation. You may run into it later on, particularly in advanced courses, or maybe sometimes in your work, where you say, gee, I just want to run a lot of random simulations and let's see what comes out of this, with a few constraints that you might have on the problem.
I didn't mention anything about this.
All right, the solution to most problems, there's really two ways you do it. You either do it deterministically, or you do it what we mean as stochastic. The beam deflection problem that you did for homework is a deterministic approach. So it means you have an equation, you're going to a unique, definite solution to this, there are boundary conditions and so forth, plug in the numbers and you get a result. When I talk about stochastic, it's basically random. So I'm not sure what's going to happen on this thing, so I have to do a large number of these samples. So your engineering problems usually have a unique number or solution. That's what we're referring to with regards, say, to the last homework problem. Most of the problems that you get here are done that way, except for the last one, the second homework that I just gave you. So another way to arrive at the solution statistically is by means of Monte Carlo. Does anybody know why it's called Monte Carlo? Yeah, it's based on Monte Carlo gaming. And so it actually stems back a long ways to John von Neumann back in the Manhattan Project. So it uses random numbers generated to simulate naturally random processes. Now these things can vary quite a bit. We do it sometimes in fluid flow. You can do it in heat transfer. You can do it in structures for that matter. Of course, radioactive decay, nuclear engineering. We did this method a lot when I worked at the Savannah River site many years ago. Making tritium and plutonium. Obviously dispersion, even quantum mechanics for those of you interested in the deep side of physics. Basically what you're doing is you use a computer. The computer then generates a large set of random numbers, and from those numbers you discern or you try to figure out, gee, what is it that's really going on in this process? Start with a sequence of numbers. These are random, so R1, R2, and so forth all the way out. So there are no correlations among the numbers. If all the numbers are in a sequence, are likely and are equally likely to occur, that sequence is uniform. Now coming up with a very good random number generator is not so easy, because if you keep running the random number generator and you keep getting the same set of numbers, you think that's random? All right, so that's why they have a great deal of input into creating truly random type of routines, particularly in MATLAB and others. The sequence, 1, 2, 3, 4, and so forth, is uniform but not random. Why? Because you can immediately recognize there's a pattern to this thing, and you can predict what the sets of numbers are going to be in the future. Now, the sequence 3, 1, 4, 2, 3, 1, 3, right, may be random, but does not appear to be uniform. Okay. So the likelihood of a random number occurring is defined as or described by a distribution function. And sometimes you'll see this as a capital PR, right? That means distribution function. So it's probability of finding a number Ri in the interval R to R plus dr, some fixed interval set, is P of x dx, right? The standard random number generator in computers usually does this between 0 and 1. So when you're doing a random number call in, say, MATLAB or MathCAD or whatever package you're using, it's always balancing things between 0 and 1. And actually, I think in the problem that I gave you in the second one, it's going to kind of put things between 0 and 1, so you'll be picking up random numbers between A linear congruent or power residue method, that's the most common way of generating a random number or a sequence of numbers. Here's a little formula down here at the bottom that you see. This is what actually goes into a number of the little subroutines and things that are called, those type of programs called by, say, MATLAB or MATLAB or MEG402 or what have you. What you do is put in a seed value, put in R1, that's a seed. You supply it. You say, I've got to start this with something, so I'll put in a seed number. Mod is a built-in function for doing some remaindering, right? So it means it's going to say, oh, am I going to be greater than 0.5, then I'll round up or I'll round down, whichever. M is the length of the sequence, A and C are constant, so let's put in some numbers here. C equal 1, A equal 4, M equal 9. We'll start with 3, right? So here's the sequence. We start with this seed value, throw it into that little formula that I just showed you. This is what you wind up with. All right, I get 4. I put that in down to here, I get 8. I take this, put it down into here, I get 6. So then if I go from 5 on to 10, this would be the sequence of numbers that I would get. The length of my sequence is 9. That's what the capital N means. After that, then it would repeat itself. So as long as I'm within 1 to 9, all right, I'm random. But if I want to go much higher than that, what's going to happen? I'm going to get a pattern. I'll get the same set of numbers that I'll start to show. How many of you played Keno? Wait a minute, how many of you know what Keno is? Okay. How many of you have played Keno before? How many of you are always looking to put patterns into those random numbers? Right? You always say, here, do the box, put 4 right here. Oh, here's a neat pattern, let's do that. What do you think your chances are of winning on Keno based on the numbers that you put in? About as close to 0 as you can get. Before using a random number generator in your program, you should check its range. That's important. And that's producing numbers that look random. You know, you can do that by inspection. If you're looking at the sequence of numbers that are coming out and you really can't predict what the number is going to be, it's probably a pretty good chance that it's random. Otherwise, you're looking at a pattern, you can immediately pick up on it and you go, well, I know what this thing's going to do later. Right? Now, Angelo Ifantis talked about probably random number generator. Did he mention that in the Nevada gaming that he uses for all the gaming that you see in the casinos and so forth?
No.
So he says it's unbreakable. You think, you know, if we ran it long enough, you think there might be a pattern?
Yeah.
I would think so.
Probably, unless he's got a billion to the billionth of whatever, but he'd never do that. But yeah, everything that man's ever written it can be broken at some point. So if you have an urge to do that, you start at the Monte Carlo side of things. Simple test of uniformity evaluates the kth moment of the random number distribution. All right, so these are little formulas. When you see things like this, it means I'm taking a set of numbers and I'm going to do a calculation or some averaging or some assessment over the range of numbers. That's what those little brackets. So here's the little formula for that. Now, if I plug this in, okay, what is it that this is actually doing? It's this. Right? That's what we mean by doing the moments, so finding the moments. I've actually developed methods in the past where I've done a lot of dispersion and fluid flow calculations where I've used 0, first, and second moments. Right? The 0th moment is the value. The first moment is its distribution. The second moment would be, well, how spread is it over a certain range? Right? So that's what we mean by moments. Another effective test for randomness, just visually inspect the values. If it looks like it's random, it probably is. Like I say, if you can figure out there's a pattern, or you can forecast the numbers out, then it's probably some sequence. They should uniformly fall to fill a square with no discernible pattern. That is, it forms a cloud. This is what we mean. Obviously, if you look at this pattern, you would say, I don't know that that's so random. I would say there's a distinct pattern there of some sort. On the other hand, if I look at this one, I just have no idea where the next one would ever crop up. So that's what we mean by filling the square. Random walk. How many of you have heard the term random walk? How many of you have been drunk before? Well, see, you've done firsthand what a random walk is. At least your friends will tell you it was pretty random, and you may even feel that way. Okay, a walker takes many steps, usually with a direction of each step independent from the direction of the previous step. So it doesn't mean that you're relying on input other than where you've been and where you're going to the next step. So start at the origin, take n steps in the xy plane. So this is what you would be doing. So you're going x, y, and all these steps. Radial distance from the starting point. It's just the sum of all these things. Remember, those are 3 dots. So this is what you would get if you wanted to calculate the radial distance. Right? The relation is valid for any walk. If it's random, the particle in question is equally likely to go in any direction. You just don't know. On average, all the cross terms vanish, and here's what you're left with. Right? So that's what that means. Know what this stands for?
Root mean square.
Root means square. What's root mean square?
Using electronics, the peak voltage.
Okay, you had it in
He
statistics.
doesn't know.
Oh, good. So we have a challenge. Go review, because I know Angelo probably mentioned root mean square.
Actually, the.
Oh, well, that's even better. Go dig it out. All right. Following steps are recommended when you produce a random walk. Choose a random angle. That makes sense. All right. You're going to go 0 to 2 pi. Set delta x equal to cosine theta, delta y sine theta. Choose a random delta x in the range minus the square root of 2 to the square root of 2. All right. Do the same thing for y. Choose random values for delta x in the range minus 1 to 1, delta y, same. Choose the sign randomly. Choose the directions, north, south, east, west, northwest, southeast, whatever it is. Randomly is the step directions. All right. Now, choose the directions randomly as the step directions is equivalent to choosing a random integer. All right, so these are just little steps that you do. Fortunately for you, when you call the program like random in MATLAB, it's doing all that for you. So it's very, very convenient, so you don't have to burden yourself with actually programming this stuff up. In the old days, that's the way we had to do it. Okay, so if the walker takes n steps in a single trial, you're going to run a total of k that's equivalent to the square root of n trials with each step, right? So you're going to put in a different seed. You're basically saying, gee, I have no idea what's going to happen. Let's do this simulation. Let's do it again with a different seed, do these combinations of simulations, and so forth, and then we'll sum up the results, see what happens. So you take the average of the results from your k trials. That's what this does right here. Calculate and output r, the distance from the origin. So what you're trying to say, okay, where is this particle going next? Plot it as a function of the square root of n for one trial, as well as the average. How many steps must be made before Gaussian statistics start to be valid? What do we mean by Gaussian statistics? Bell curve, right? Normal distribution. So ideally, if you do enough of these things, everything falls within the bell curve. Sometimes you can't run an infinite number of simulations. Okay, check the seed to see if you've obtained the expected statistical error band right here. So that would be square root of r is equivalent to n to the 1/4 power, right, for large values of n. The walk is random, a scatter plot will show no preferred direction. This is what's going on. Start here, go here. Random, okay, go there, go there, go there, maybe there, there, and so forth. So this is where the particle would end, or the person that would be walking. This would be the r that you would calculate. All right? Notice, I'd say that's pretty much a random distribution. Okay? So here's what's going on, starting right here. Who knows through that circuitous path what's happening, winds up finishing there. Now, when you plot these things of r versus the square root of n, then that's what you would expect, theory-wise, right? Because if you do enough of these simulations. what happens on this is that you get something that looks like this. Why is this? Because we didn't do enough. If we did a lot more simulations, it would fall on that curve. All right, now I've put in a program for a random number generator. It'll be on the slides. You can see it as we go through some of this stuff. Now this one happens to be, what kind of language? That's good stuff. Yeah, I use that probably. That's a Fortran code. So I thought I would at least put something up there that would say that you were introduced to Fortran. But in looking at the Fortran, it requires you to kind of think out the logic. It's fairly close to pseudocode. So from the pseudocode, you can do, now from the Fortran code, how many of you could write a MATLAB code?
I'm not sure what your mod is.
Module. Yeah. It's the same call in MATLAB.
Oh, they still have that in MATLAB?
With probably about staring at this for maybe 10 minutes or so, I'll bet you could begin to say, oh, I know how to put this together because I see the logic and I can then write a MATLAB code. The nice thing about MATLAB, it's a higher level language instead of Fortran. But believe me, when you leave the university and you get outside working for a company, more than likely they might give you a Fortran code and have you, why don't you rewrite this in MATLAB or bring it up to date. Here's a random walk. Nice thing here is you can put in little comment lines that says, okay, in this particular part of the loop, this is what we're doing. Set parameters, so forth. This is also a simple Fortran.
This is like me free pack?
Yeah. So this program would actually do the random walk for you. Okay, oops. That's the other part of it. Now, what you will find in doing a Fortran code on something like that, it requires quite a bit of programming, lines of programs, versus doing it in MATLAB. My guess is that you can do that in about 5 lines or less in MATLAB. This was one of the example problems that I had in here. I won't go into this in any detail. There's just too much that goes on with determining parameters and so forth that I don't want to spend a lot of time on. But you can do that at your leisure when you access the website. It's basically calculating, you've got some probabilistic type values for the loads and so forth, and then so then running that over some random number generation, it says, okay, this is what we expect. It's kind of like doing an inverse problem where you have some results, but you're not quite sure what the density of something would be or the conductivity, and so you're trying to back calculate or figure out, gee, what would the values be that would produce these particular results. So ultimately, you're calculating mean values and all sorts of things like that. So this is what we were looking for as far as the results. Instead of doing it deterministically, we were doing it in a stochastic random approach and doing enough simulations that it begins to start looking, oh, this is where what I think the value is going to be. All right, radioactive, yeah.
By simulations, you mean we guess some of the parameters in the equation and then we just run a test to see if that's what happens?
It works like this. So you have a problem with some constraints, right? Like the constraint of this room might be the size of the room. So I know that I've got certain parameters on a problem. But what I don't know, let's say I have a particle in this room and I want to know, is it going to go here or there or whatever? I'd probably do it randomly. All right, so then I would keep it, I would have that particle do whatever it is randomly based on the conditions of the room and the size, and then just run it. And if I do enough of these things, I would probably find that it's, in general, they're probably all grouping in one particular area or something. All right, radioactive decay. Spontaneous decay, natural process. Particle decays into other particles. If I have uranium-235, right, unless I split it, what's it going to do? Yeah, it's going to decay, right? You can tell them all about nuclear decay, right? It does all sorts of things. All right, the exact moment when any one particle decays is random. It doesn't matter how long the particle's been around, it's what is happening to the other particles, or what has been happening to the other particles. Probability P, the particle decaying per unit time is constant. When the particle decays, it's gone forever. That's radioactive decay. Number of particles decrease with time, so does the number of decays. So what's the probability of a particle decaying in some time interval? Same or the constant as long as the particle still exists. Right, so this is the formula that is used. So delta n is the number of particles that decay in some small time interval. These are the number of radioactive particles at time t. The probability of any one particle decaying can be written like this, just almost common sense. Delta n over n. And it turns out we can equate that. And so we set it to a minus lambda delta t, all right? What's lambda? Decay rate. Okay, what's, by the way, what's the half-life of plutonium? 230 million.
1 to the 6?
25,000 years. What's the half-life of tritium? You know what tritium is? 12 years, a little over 12 years.
I knew that.
Now, does everybody know what plutonium is? Right? Okay. Do you know what tritium is?
I have no idea.
What's tritium? What does it sound like? Where does it come from? H3. Hydrogen. What's it used for?
Extra neutron.
That's all it is.
You surround an atomic bomb with tritium, basically. And what it does is give the boost to make it a hydrogen bomb. How many of you have watches that glow? Or you got one?
It will set
No,
off.
none? Okay. I mean, it glows on its own? What makes it glow?
Radiation?
Yeah.
Well, it glows because it absorbed energy and it goes to the next quantum level. And as it decays down to its stable quantum level, the visible light gives off.
Tritium. That tritium comes from the Savannah Riverside. Every watch that glows like that has a little minuscule amount of tritium gas. Okay, that equation you're going to write as a finite difference equation. Delta nt and delta t are experimental observables. All right, it cannot be integrated like an ODE, but it can be solved numerically. That's why you did methods called Euler methods. All right, those forward marching techniques. The decay process is random. You cannot predict an exact value for delta n of t. So, you wind up that equation. You have continuous decay. That would be the number of particles as n goes to infinity. So you wind up getting this thing. All right? I can integrate this equation. That equation, that's that equation. All right? I can take derivatives, obviously, but that's what I'm after. In the limit, we get exponential decay. Decay rate, lambda is the inverse. So that's the lifetime, 1 over tau. Right? That's what I was referring to with half-lives. So if I have plutonium and it decays in 25,000 years, half of it's gone, another half, another 25,000 years. How long does it take before something eventually just decays away? How many lifetimes? Half.
Several.
Take a guess. 8. All right. Exponential k is a good description of nature only on the average. All right. As the number of particles decrease, the equation becomes less accurate. Now, this is, you know what this is called? It's a flow chart. Does it look like a flow chart?
Yeah.
How many of you heard the name or have seen flow charts before?
Once, twice.
All right. Where did you see them?
TM.
CSC 117.
Computer science. For those that have been through computer science, that's what you'll see. Now, those boxes or those shapes denote something. So whether you're inputting data or reading data, you're outputting results or whatever, a logic, this is a decision tree, all right? Am I going this way or am I going this way? Each one of those things means something. So you can actually take pseudocode and you can do a flow chart. When I did my first book many years ago, Finite Elements, they absolutely insisted that I include flow charts on the programs. So I doubt if anybody today even takes a glance at flow charts. But in those days, probably 15, 20 years ago, you had to do everything as a flow chart first. All right, so this is pretty much pseudocode, kind of tells you what's going on. That's all of this is doing that. That's all it takes. Now, what I wanted to do, actually this was an assignment that I gave the class last year, but I'm not going to do it with you guys this time. So I wanted them to do some radioactive decay simulations using a Monte Carlo. And I wanted them to see how close they could come to producing results like this, as far as radioactive decay. So the log of n versus time. All right, now what's going on here? What does this mean? All right, number of simulations that I'm doing, what does that tell me? What is it that you can grab out of this chart? What is it that you really have to do to get a good simulation?
Lots of samples, lots of samples.
Yeah, see this? That's what you're after. So even at 100,000, it's pretty good, right? But maybe I'd want to do 500,000 or whatever. But basically, the more simulations that I do, the better I'm going to get as far as what the true process is, all right? The number of nuclei is large. Now, you see what it says? But stochastic for the log n less than 2. That's what this means down here. It's just random. We have no idea, really. We're not very good. We just haven't done enough of these simulations. So that's what's happening in these things. So as we start doing a whole lot of these things, right, we can start to get better approximation. Now, let's put this in perspective. How many of you have taken a coin and flipped it a number of times? More than likely, you will find that you would have gotten more heads than tails or vice versa. Right? If you've done that, say 10 times, flip a coin 10 times. You know that if you do that an infinite number of times, you're going to get what?
The same number.
Yeah, it's going to be exactly 50%. So you flip the coin, you're going to stop. What do you think happens in casinos? Right? I guess if you gamble an infinite amount of time, you probably break even. Nice try, but maybe not quite. All right, now I'm going to show you the random walk convection dispersion model. This is a technique that we've been using for some time. That actually we use to calculate species concentration. And so we're taking particles and we're advecting these things. That's why it's called random walk advection dispersion. Advection means the movement, like from wind. Dispersion, turbulence, or diffusion. So this is the little formula. X denoting the position of where the particle is. Then it's equal to the previous position and time where it was, plus some delta x plus z. All right, z is a random displacement. So that's just a random number or something that we throw in. If you look at problem number 2, what I've done there is just call it noise. All right, so I want you to do it only for one particle. So this is the little formula that we tend to use. All right, so these are particle coordinates. All right. Where does that come from? Does anybody know what the difference between Eulerian and Lagrangian coordinates?
One has to do with partials, and then the other one has to do with
Think of it, an easy way to remember is if you are looking at the wind tunnel in the multifunction lab, there's the test section. You've got air that's blowing through and out, and you're looking at the window. So here's this little cutout. That's an Eulerian frame of reference. That's your little control volume Things are coming into the control volume, they're going out, you're watching just what's in that control volume. On the other hand, if you're Lagrangian, you're setting on the little particle itself. So you're going, taking a ride with the particle. So wherever that particle goes, that's what you're doing. So you're tracking that particle. That means our frame of reference is now on the particle instead of in the control volume. All right, now, Shalene, you want to talk just a few minutes about what you've been doing with regards to dispersion?
This is a test case we have been done by using the random walk vector diffusion model for simulate indoor contaminant dispersion. This is especially valuable if you deal with some like homeland security and emergency response problems. Let's see how the problem is. This is the standard office complex setting. This is the secretary's room and the manager's room with some tables sitting inside the room. Suppose we have a terrorist who want to do some the doctor maybe.
They're disguised as firemen, you have to be careful.
Yeah, put some contaminant sauce somewhere inside the room. And the most important thing right now is to decide how the contaminants will be dispersed inside the room. This is the boundary condition setting based on the ventilation condition for the inlet and outlet. And this is the initial computational mesh we have been using for. We use the finite element method. And if we choose different contaminant source location, you will see that the dispersion pattern will be different. And the most important thing is try to find in which location is the most safety place. For example, if the contaminant source is in the upper side of the room at this corner, so the most safety place, relative safety place will be here and here. But things will be different if the source location is changed from top to the lower part of the room. As you can see that this lower part becomes the most dangerous part.
Is that because you're excluding the desk all the way up to the ceiling?
Yeah,
Because that's actually a harder path to follow, and it should disperse and go across, and then it should expand and then go back through the window.
yeah, it's a kind of follow the flow pattern. But remember, we have the random dispersion, which comes from the turbulent effects. Okay, so that not exactly follow how the flow will go to, but they'll get some dispersion.
It's really a 3D problem. We're just giving you a slice, kind of at desktop level. Right.
Sorry.
Oh, okay. I'll talk about the homework.
Thanks.
That's good. The important thing about these pictures, if you're the manager or you're in this inner office, and somebody says, ooh, there's a release or there's something going on here, and you get up from your desk, which way are you going to go?
Out the window.
Out the window. That's good, because that stuff will follow you as you go out.
Yeah, you'll drag it with you.
Well, would you rather have it follow you, or would you rather head through to it out the door, you know?
Well, yeah, the point is, if you're here, and the source is here, then to evade it, you would want to do this. If you're here, right, you don't want to go around this way, because you'll run right into the plume. So you'd want to go out this way.
But the point is, if someone says there's like a gas infestation, you're not going to know what direction it's coming from.
That's
Throw your
why.
chair out the window.
That's why we're developing these techniques in ways in which it would instruct you smart rooms that either can turn on ventilation or it can adjust or direct you so that you know how to get out. When we had the popcorn dispersion in here and everybody smelled it, I think I remember asking, how would you get out of the room? Some of you would open up the back door. Some of you would probably go out this way, even though you'd be going into the plume. What happens when you open the door?
It just sucks it out.
The advection, the velocity enhances. And so this stuff starts moving towards the door. And it can actually pass you by, right? So you can still get engulfed into the plume. All right, now the homework.
Authorization basis.
Here's the first homework problem. You have actual data that was taken in a tunnel. You got velocity and force, or the drag. Now, in the real world, as they say, you measure things in miles per hour and pound force.
Yes.
You're going to see in that problem that I've got MKS units, so you're going to have to do a little conversion. The drag on the car is given by, I give you the formula, and the density is 1.2 kilograms per cubic meter per air. Well, you're going to have to get the units right. The frontal area is 1.5 square meters. So what I want you to do is determine the drag coefficient and to watch your units. Just like the Mars lander some years ago.
Yeah, oops.
Right. Right.
There's
It landed one time. All right, second homework problem. You have a particle in a room. How likely is the particle to hit the east wall of the room? All right, so what you do is it's basically a box. That's what I want you to model. This is the equation right here. It looks just like the one that I showed you for the random walk that Shaling and I have been doing for some time. Right? F of x, that function, is k over x squared. So it's an inverse proportion. Right? It's proportional to the inverse of the distance squared. That's what we're doing with regards to that particle placement. Western wall is x equals 0. The noise is just epsilon times a random number. That's what I want you to do, is to calculate that random particle. That varies between -1 and 1. The eastern wall is 5. Western, all right? Sorry, the eastern wall is taken at x equal 5. The constant proportionality, use k equals 0.5. You have a noise amplitude of 1. So that means at k equal to 5, x equals 0, amplitude 1. I want you to run at least 200 experiments. All right, that means simulations. I want you to determine how many runs it takes to reach the eastern wall for that particle. And you should plot the results. So you're going to have a particle, you're going to set it out, it's going to be random. You may have a number of these things that are going to hit the western wall, whatever. How many are going to actually get to the eastern wall? All right? Does everybody understand?
So
What you will do will be to run a random number generator. You can do that from MATLAB or MathCAD or what have you, or you can pull from one of the code listings that I have there in the slides. Right?
Where is the particle positioned in the room initially?
X equals 0 is where you're going to start. All right? So you start here. The eastern wall is at x equals 5. You just plug it in and just start running it.
So it's just a 1D problem.
Yeah, it's basically just a 1D type of thing. All right, does everybody understand?
So will the answer we're looking for be a number between 1 and 200? Like how many of our simulations?
Yeah, how many
take
times or how many of the simulations showed that you actually reached the east wall? Okay.
Do you want x equals exactly 5, or would 4.7 or 4.8 be kind of acceptable?
Why would you want to do that?
Well, because, I mean, like, if it's close to the eastern wall, and you're a person standing at the eastern wall, it just,
Either hits the wall or it doesn't.
okay.
All right? You don't want to fudge on it. All right, so think of it just exactly like the popcorn experiment, but now you're trying to say, okay, there's one particle of that popcorn. What's it going to do? By the way, I noticed in the syllabus there was a quiz scheduled for next Tuesday. Do you want to do the quiz next Tuesday, or do you want to do it after Thanksgiving?
After Thanksgiving.
Right. If we do it after Thanksgiving, it would be that Thursday,
All right, thanks.
because I would do the review for the exam on Tuesday.
Yes.
All right? Now, this Thursday, we'll talk about PDEs, and we'll do the same next Tuesday. Then the following Tuesday will be a review for the second exam. Now remember, time is crunching, so you'll only have really a week of lecture after that, and then we're done. All right? So you want to do it then the Thursday after Thanksgiving?
Yes.
Okay.